In this video, we will take an up-close look at the mechanical and electrical components of the SPARKY 2 system. The SPARKY 2 system, seen here, is the result of a robotics engineering semester project. The project was sponsored by the MSPE, or Michigan Society of Professional Engineers. The MSPE expressed a need for a robotic demonstration system that exceeded the limitations of the original SPARKY 3000 robot. A team of 4 mechanical engineering students were selected to complete the project. Everything you see here was fabricated by the students. All of the design, welding, machining, wiring, and programming was completed by the students during a single semester. Now that we know the background of the project, let's go in for a closer look. We will begin with joint 1, also called the shoulder rotation joint. The robot is attached to the cart by means of a 3/4 inch steel shaft that connects the robot to the drive motor mounted below the cart. The weight of the robot is supported by a thrust bearing mounted under the robot. The radial forces that result on the shaft due to the outstretched arm are supported by a radial bearing near the motor coupling. The motor that drives the shoulder rotation is a 3-phase AC gear motor. As seen here, the motor is coupled directly to the shoulder shaft via a solid coupler. The control system tracks the position of the joint via a potentiometer. The nylon gear seen here is mounted to a potentiometer. The nylon gear is driven by a steel spur gear mounted on the shaft. Let's move on to the next joint. Joint 2, also known as the shoulder elevation joint, is driven by a 3-phase AC gear motor. The output shaft of the drive motor is coupled to a secondary worm gear drive via a flexible shaft coupler. As seen previously, the potentiometer for this joint is driven via 2 spur gears. Also, this is the first counterweighted joint. Approximately 30 pounds of counterweight was needed to meet the factor of safety requirements of 5 or higher. Let's move on to the next joint. Joint 3, also known as the elbow elevation joint, is driven by a 24-volt DC gear motor. The motor drives a worm that essentially walks up and down a mounted worm gear. This joint is also counterweighted. Approximately 18 pounds of counterweight counter the torque produced by the weight of the end effector and the payload. As seen previously, the potentiometer for this joint is driven via 2 spur gears. Let's move on to the next joint. Joint 4, also known as the wrist elevation joint, is driven by the 24-volt DC gear motor mounted to the left of the joint. The potentiometer for this joint can be seen mounted to the right of the joint. This is the first joint that makes up the end effector or hand of the robot. In the original design for this joint, the drive motor was completely enclosed within the joint. Unfortunately, due to an inaccurate specification given by the motor supplier, the motor had to be mounted in its current position. Moving on. Joint 5, also known as the wrist rotation joint, is driven by a single-phase AC gear motor. A series of spur gears transfer the motor torque to the drive shaft. The joint can rotate up to 270 degrees, which is limited by the available travel of the potentiometer. The final portion of the end effector that houses the gripping mechanism can be easily removed by simply loosening a couple set screws, unplugging the motor connections, and sliding off the drive shaft. The end effector was designed this way to accommodate future end effector revisions. Let's move on to the gripper. The gripper is opened and closed via a 12-volt DC gear motor mounted to a rack and pinion system. This design was inspired by a Mitsubishi MoveMaster EX training robot that is used in the lab. The MoveMaster EX uses a similar system, but uses a servo motor instead of a DC gear motor. The racks are mounted to slides that run along stainless steel guide rods. The two fingers of the robot are mounted to carriages. Originally, we planned to grip objects by stalling the motor to grip. We soon found that even though we were operating well within the specifications of the motor, that the tiny brass gears couldn't take it. As a solution, we added the sandpaper to the surface of the fingers to increase our coefficient of friction. In order to protect the motor, we added a limit switch to the gripper that will stop the motor once the payload is gripped. Also, there is a redundant timer in the control program that will stop the motor in case the limit switch is not activated. Next, let's take a look at the control system. Here we can see the control system mounted in the onboard control cabinet. The brains of the system is an Allen Bradley SLC 500 PLC. As you can see, we have various input and output cards mounted in the PLC chassis. Here you can see the 10-volt DC power supply that is used to power the potentiometers and the gripper motor. Here we have the primary system fuse, the primary DC power supply, the MCR or safety relay. These are the relays we use to control direction and activation of the motors on joints 3 through 5 and the gripper. Here we see the VFD for joint 1 and the VFD for joint 2. And here we have the DC speed controller for joint 3. Looking back at the PLC, we can see the basic card. This card contains the basic processor that runs the main control program. This concludes the up-close look at the SPARKY 2 system. If you would like to learn more about this project, visit the SPARKY 2 website at www.gvsu.edu/engineering and look for the SPARKY 2 project under Student Semester Projects on the left navigation menu. Thank you.